Welcome to our latest video on the topic of phenol. This video is suitable for A-level students. By the end of this video lesson, you should understand that phenol is a very weak acid and will react with sodium hydroxide but not sodium carbonate. You should also be aware that phenol reacts with acid chlorides to form esters and be able to write chemical and word equations to describe these reactions. And finally, you should understand that neutral iron 3 chloride and bromine water can be used as chemical tests for phenol and be able to write an equation to describe the reaction with bromine. Now, phenol has the chemical formula C6H5OH. And phenols, just like alcohols, occur widely in nature, and in phenols, the OH group is joined to a benzene ring. And phenol is a functional group in itself, and it's completely different to alcohols because it has different reactions and different properties. Now, an example of a phenol is vanillin, and this is found in the seed pods of the vanilla orchid, and it's widely used as flavouring in foods like chocolate or ice cream. And the structure of vanillin is as follows, and you can see it's classed as phenol because it's got a benzene ring attached to an OH. Now, phenol is a solid at room temperature and has a melting point of 40.5 degrees C and a boiling point of 181.7. And phenol has lots of different uses. It's used to make plastics, it's used to make drugs, it's used to make explosives, and it's used to make cosmetics, and it's produced in large quantities from petroleum. Now, phenols have different properties to alcohols. That's why they're classed as a completely different functional group. Now remember, the functional group of a molecule is the part of a molecule that determines its chemical reactions. Now, there are differences in the chemical reactions that phenols undergo compared to alcohols because the lone pairs of electrons on the oxygen can spread over the benzene ring in phenol and make the CO bond harder to break. Now, phenol is more reactive towards electrophiles than benzene because lone pairs of electrons on the oxygen can get delocalized into the ring, and therefore the ring becomes more attractive to electron pair acceptors. Now, the other big difference between phenol and alcohols such as ethanol is that phenol is more acidic than water and alcohols are less acidic than water. Now, phenol is classed as a very weak acid and it reacts with sodium hydroxide to form the salt sodium phenoxide, but it's not acidic enough to react with sodium carbonate. So if you add sodium carbonate to phenol, you will not observe fizzing in the same way that you would if you added it to a carboxylic acid. This is because sodium carbonate does not react with phenol to form a salt, carbon dioxide and water like carboxylic acids do. Now, a chemical equation is shown here to show the reaction of phenol and sodium hydroxide. So phenol plus sodium hydroxide would form sodium phenoxide and water, and sodium phenoxide is a soluble salt. Now, in the first part of this video, we're going to look at phenol's acidity. So before we do that, it's important to test your understanding of acidity from Year 11 and Year 12 chemistry. So read through the questions, pause the video, have a go at them, and then we'll go through the answers. So now let's go for the answers to questions 1A and 1B. Now, 1A is asking for the definition of a strong acid. So a strong acid is a substance that totally splits up into H+ ions when you put it in water. Or you could say it's a substance that totally splits up into protons when you put it in water, because a H+ ion is also known as a proton. Now, for question 1B, you're asked to give two examples of strong acids. So you could say hydrochloric acid or sulfuric acid or nitric acid. And I've shown you here the equations to prove that hydrochloric acid and sulfuric acid are strong acids, because you'll notice that they totally split up into H+ ions when you put them in water. And notice that it's a single arrow. It's not reversible because every hydrochloric acid molecule and every sulfuric acid molecule totally splits up into H+ ions when you put it in water, and they don't rejoin to reform the acid. Now question 2a is asking you to define the term weak acid. Now a weak acid is a substance that partially splits up into H plus ions or protons when you put it in water. And an example of a weak acid is ethanoic acid. You could also say propanoic acid, butanoic acid, or you could also say phenol, which we're going to talk about today. And I've shown here an equation to show the ethanoic acid molecules breaking up into ethanoate ions and H plus ions. And you'll notice that an equilibrium is set up. The reaction is reversible. And typically, in every 1,000 molecules of ethanoic acid, around 4 stay split up at any one time. So the equilibrium is very much on the left-hand side here. Now you should remember from year 12 chemistry that the pH of a solution is a measure of the concentration of H plus ions. And the lower the pH, the more H plus ions are in solution. And if you think about ethanoic acid splitting up compared to hydrochloric acid splitting up, if I had 1,000 molecules of hydrochloric acid, I would have 1,000 H pluses because they would all split up. And typically, for every 1,000 molecules of ethanoic acid, there's only about 4 split up at any one time. So you can see that there's a lot more H plus ions produced from a strong acid than a weak acid. Now question 3 is asking you to explain the Bronsted-Lowry definition of an acid. Now this was covered in year 12. Bronsted-Lowry define an acid as a proton donor. So we're now going to look at why phenol is more acidic than water. Now when you put phenol molecules in water, they split up into phenoxide ions and hydrogen ions. And an equation is drawn here to show phenol splitting up into phenoxide ions and hydrogen ions. And it's classed as a weak acid because it partially splits up into H plus ions when you put it in water. And phenol is a lot less acidic than carboxylic acid such as ethanoic acid. Now in ethanoic acid, I said that for every 1,000 molecules there are about 4 that are split up at any one time. Now it's much less for phenol. There's about 1 in every 1,000 molecules. So there's less H plus in solution in phenol than in ethanoic acid. However, phenol is still classed as a weak acid because it partially splits up into H plus ions. However, it's not as strong a weak acid as ethanoic acid. Now to show why phenol is more acidic than water, I've drawn 2 equilibrium here. I've drawn phenol splitting up into a phenoxide ion and hydrogen ion, and I've drawn water splitting up into hydroxide ions and hydrogen ions. And the reason that phenol is more acidic than water is because the phenoxide ion is more stable than the hydroxide ion. Now the more stable the anion here, the less likely H plus ions are to attack it and recombine with it, and therefore the more H plus ions are in solution. And remember, the more H plus ions in solution, the more acidic the substance. So the phenoxide ion is more stable because lone pairs of electrons on the oxygen can get spread into the benzene ring, and this means that the negative charge on the oxygen is spread out over the benzene ring. So therefore the negative charge is not completely on the oxygen in a phenoxide ion. This makes the ion more stable, the H plus less likely to attack it, and that's why there's more H plus ions in solution, and that's why phenol is more acidic than water. Now in the case of a hydroxide ion, there is no means of stabilizing this ion. So that's why phenol is more acidic than water. It's because the phenoxide ion is more stable than the hydroxide ion. And it's the anion stability that determines how much H plus is in solution and how acidic the substance is. Now alcohols are less acidic than water. And I've drawn the equilibrium here of water splitting up into hydroxide ion and hydrogen ions, and I've drawn ethanol splitting up into ethoxide ions and hydrogen ions. And the reason that ethanol is less acidic than water is once again to do with the anions. An ethoxide ion is less stable than a hydroxide ion. And this is because the alkyl group in the ethoxide ion pushes electrons onto the oxygen, and that makes the ion less stable. Now, if the ion is less stable, it's more likely that the H plus ions will attack it and recombine with it, and therefore push the equilibrium to the left. So the ethox ion is less stable than the hydroxide ion because in the ethoxide ion the charge is on the oxygen because the alkyl group is pushing electrons onto the oxygen, and therefore if the ion is less stable, there are less H plus ions in solution because the H plus ions are more likely to attack it, and therefore if there's less H plus ions in solution, it's less acidic. Now the order of acid strength here is phenol is the most acidic, then water, then ethanol, which is the least acidic. Now we've discussed stability before when we talked about benzene, and we talked about the fact that benzene is able to spread out its electrons, which means it's less likely to be attacked by electrophiles compared to alkenes. Well, this is the same principle here. If the charge is on the oxygen in one place, it's vulnerable to attack by H plus ions. If there's a way of spreading out this charge, so like in phenol where the charge can spread over the benzene ring, it's less likely to be attacked by the H plus, and therefore it's more stable as an ion. In the next section of this video, we're going to look at the reactions of phenol, and the first reaction we're going to look at is the reaction with bromine. Now when phenol reacts with bromine water, you get a white precipitate. Now the bromine water decolorizes, it changes color from orange, it loses its orange color, but you get a white precipitate, which is very different to bromine water reactions with alkenes, where you don't get a white precipitate. Now the reason you get a white precipitate is because the bromine reacts with the phenol and forms 2,4,6 tribromophenol. Now the reaction is electrophilic substitution. Now this reaction and this observation of a white precipitate when you add bromine water to phenol can be used as a chemical test for a phenol functional group. Now phenol undergoes electrophilic substitution reactions more readily than benzene. For example, when you add benzene and bromine, you only get a reaction if you have a catalyst to make the electrophile. And when you do get a reaction, you only get one bromine atom substituting on the ring. Now, if you have phenol, you get multiple bromines on the ring, and you don't even need a catalyst for the reaction to work. Now, the reason that phenol is more susceptible to electrophilic substitution is that the lone pairs on the oxygen can spread into the ring, delocalize into the ring, making it more susceptible to reactions with electron pair acceptors, electrophiles. And you get multiple bromines on the ring, and that is evidence that it's more susceptible to electrophilic substitution reactions. Now when electrons move towards atoms or away from atoms via single bonds, that's called the inductive effect. And when they move towards other atoms or away from atoms via double bonds, that's called the resonance effect. So in benzene, electrons are moving into the ring via a single bond, and this is an inductive effect. Now the addition of bromine water to phenol and the fact that it decolorizes the orange solution and gives a white precipitate is the reason that bromine water can be used as a chemical test for phenol. Now, the presence of a phenol group can also be tested for by the addition of neutral iron 3 chloride solution. And if you add neutral iron 3 chloride solution to any compound that contains a phenol functional group, you will get a purple or violet colour. Occasionally, you will get green or red, but the usual colour is either purple or violet. And that is the test for phenol. Iron 3 chloride added to phenol gives a purple or violet coloration. Now, it's important to mention that alcohols do not react with either bromine water or neutral iron 3 chloride. So you could use either chemical to test between an alcohol and phenol. Now, the second reaction we're going to look at with phenol is esterification, reactions that make esters. Now, phenol reacts with acyl or acid chlorides to form esters in the same way that alcohols do. However, it's important to mention that phenol does not undergo esterification reactions with carboxylic acids like alcohols do. So my equation here shows benzoyl chloride, an acid chloride, a benzene ring attached to a C double bond OCl, reacting with phenol to form the ester phenyl benzoate and hydrogen chloride gas. Now, in this reaction, the hydrogen atom, which is attached to the oxygen in phenol, bonds to the chlorine of the acid chloride to form hydrogen chloride. Now, this results in an ester forming, and the oxygen in the ester that's attached to the C double bond O has come from the phenol. Now, this ester is named as phenyl benzoate because there's a benzene ring attached to the oxygen next to the C double bond O, and a benzene ring is also called a phenyl group. So this compound is called phenyl benzoate because the rest of the ester resembles benzoic acid. So the ester is called phenyl benzoate, and my other product is hydrogen chloride gas. Now, when phenol reacts with acid chlorides, a catalyst such as pyridine is often used, which is a base, and this reacts with hydrogen chloride that's formed. And you have to be careful which base you choose, because if you use sodium hydroxide, there would be no reaction at all because the NaOH would actually react with the acid chloride. So therefore, pyridine is chosen as a base because it doesn't react with the acid chloride and it just reacts with hydrogen chloride, and that just speeds up the reaction. So now we're going to test your understanding of this topic with some practice questions. So here's our first practice question. Read through the question, pause the video, have a go at it, and then we'll go through the answers. So this first question is asking you to complete the following chemical equations and name the esters formed. Now, for each of these, a hydrogen on the OH group of the phenol molecule is reacting with a chlorine from the acid chloride, and this forms hydrogen chloride, and then the oxygen that's attached to the benzene ring joins the remaining part of the acid chloride, and you get your ester. So in question 1a, I have the ester phenyl ethanoate formed because if I look at the ester closely, I have a benzene ring attached to the oxygen next to the C double bond O, and a benzene ring is a phenyl group, and the rest of the ester resembles ethanoic acid, so therefore the ester is phenyl ethanoate, and my other product is HCl, hydrogen chloride gas. So for part B, I have the acid chloride butanol chloride reacting with phenol. So the ester I'm going to make is phenyl butanoate and hydrogen chloride gas. Now, the ester is called phenyl butanoate because if I look at the oxygen next to the C double bond O, it's attached to a benzene ring, a phenyl group, and the rest of the ester resembles butanoic acid, so that's why the ester is called phenyl butanoate. Now for part C, I have the acid chloride, pentanol chloride, reacting with phenol. So the ester will be phenyl pentanoate, and it's called phenyl pentanoate because if we look at the oxygen next to the C double bond O in the ester, we have a phenyl group, a benzene ring attached to it, and the rest of the ester resembles pentanoic acid, so the ester is called phenyl pentanoate. And we have hydrogen chloride gas again produced as the other product. So here are questions 2 and 3 for you to have a go at. Once again, read through the questions, pause the video, have a go at them, and then we'll go for the answers. So question 2 is asking you to state what is seen, if anything, when aqueous phenol is added to aqueous solutions of the following reagents. So if you add iron 3 chloride to phenol, you will see a purple colour, a purple solution, so 1 mark for that. And if you add sodium hydroxide to phenol, you make sodium phenoxide, but that is a colourless solution, so you would see no change, you see no observation there. So question 3 is asking you to come up with a chemical test other than the use of an acid-base indicator to distinguish between methyl propanoate and phenol. Well, phenol can be tested for using neutral iron 3 chloride, and it would go purple with phenol and no reaction with methyl propanoate. Now the alternative to this is to add bromine water, and phenol will give you a white precipitate. It will decolorize the bromine water as well, but you get a white precipitate. While methyl propanoate would just decolorize the bromine water because it's got a carbon-carbon double bond, and it will not produce a white precipitate. So there's 1 mark for the reagent and 1 mark for the observation. So that concludes this video lesson. So after watching this video, you should now understand that phenol is a very weak acid that will react with sodium hydroxide but not sodium carbonate. You should be aware that phenol reacts with acid chlorides to form esters and be able to write chemical and word equations to describe these reactions. And finally, you should understand that neutral iron 3 chloride and bromine can be used as chemical tests for phenol, and you should be able to write an equation to describe the reaction of phenol with bromine. So that concludes our video. Please check out our YouTube channel, Dr. O Chemistry, and our Twitter site, which contains lots of chemistry information and links, @RadaChemistry.